This is a continuation for section 11.1, which is separable differential equations. And by separable, we said that we can write them in of the form, factored form of some type, where one would be x's and the other one would be y's. And we've done a couple of these problems in class. One that I wanted to touch on is called a logistic growth model. So this is a separable one. A different one is, this one is still separable, but finding the solution to it, as we've talked about before, is not necessarily easy. And in this class, the only ones we can solve are the separable ones. This one is also separable, but the integral, when you integrate it, does not come out to be neat, and you need tools that we have not learned of. And so if we have something of this form, if you were able to separate it, actually you can't separate it, if you're able to actually integrate it, what you would do is, and I'll erase this momentarily, you'd have dy divided by, we can leave the k, all the y's come to this side, k dt. The problem is when I try to integrate this, I can integrate this part on the right all day long, that's fine. This one, however, has this weird denominator that we have not discussed how to integrate something like that, and that's where it gets messy. So I'm going to take this out, and we're going to assume that we've done some magic math, and the solution to this differential equation ends up being that y is equal to n over 1 plus b e to the negative kt. Now this, of course, will be given to you. I would not expect you to memorize this. And b is a little complicated. It's actually n minus y0 divided by y0, where y0 is the initial condition. So think of it as, y0 is the same as y of 0. It's the initial value. Now graphically what this means is, this is a logistic growth model, so we should probably call it that. And what that means is, if we have our x and y axis here, in this particular case, you'll have an asymptote at the 0, at the x-axis there, and the graph will kind of do this curve. This value here is our y0, and actually I'm going to copy this and shift it slightly over, and you'll see momentarily why that is. So now this value here where it crosses the y-axis there, that's y0. This value up here is n, and you can see the logistic growth model is meant really to model animals, for example, maybe bacteria or something. There's going to be a carrying capacity of some type. That's where your n is. N is the maximum that this population will be. Obviously, if it keeps growing exponentially, as we say, oh, this grows exponentially, there's a cap. It can't just grow to be infinite. And so that cap is maybe because of the size of the area that it's in, or maybe how much food it has, or who knows what the limitations are. But there is a limitation, and that's what n is. N is the maximum this population, if you will, can be. B is just a constant based on this that we have right here, and k is the growth factor. Just like how fast it's growing. So k is like a growth factor, or growth rate. Okay. And so this is the differential equation, and then this here is the actual solution to it. Another application of differential equations is Newton's law of cooling. Newton's law of cooling has this differential equation. Notice the difference in the case, capital T versus little t. Capital T is temperature, little t is time. So dt dt is equal to negative k t minus t sub m. And so this is out of one of your problems in your book. You're told that Newton's law of cooling states that the rate of change of temperature of an object is proportional. So the rate of change of temperature of an object is proportional, just means we put it in a k, to the difference in temperature. So difference is subtraction in temperatures. So the difference in temperature between an object, which is T, and the surrounding medium. So this is temperature of the medium, meaning your environment. Thus, if T is the temperature of an object after little t hours, and T sub m is the constant temperature of the surrounding medium, then we have this differential equation. So the where that it comes from is important, and that people just did experiments and noticed this relationship. And to solve this, the solution is T is equal to C, which is again some arbitrary constant, e to the negative kt plus T sub m. And again, T sub m is surrounding temperature T is the actual temp of the object. K's and C are constants, so they don't change for the problem or for the material that you're dealing with. So for example, if I were to take out a pie from the oven, that pie is going to have the same K value. The C is just a constant of integration, so it just depends on what's going on there. And little t is just time. And now the time is not like an SI where it has to be in seconds or any specific unit. It's whatever unit you're given. So if the problem tells you it's in so many hours, then t becomes hours. You can change it to whatever you want based on the problem. Just stick with the same unit. So if they give it to you in hours and they ask you what happens 30 minutes later, since you started with hours, 30 minutes will then become 0.5. With this equation, try some problems out, and that's probably what we'll do this week. And then the next video will be the multivariable calculus part.